In this video, we're going to go over gravitational potential energy. It's defined as the energy stored in an object because of its position in a gravitational field. And like all energy, it's a scalar value and it's measured in joules. The formula we're going to use is delta potential energy is equal to mg times delta h. So m is going to be the mass, always in kilos. G is the gravitational field strength. It's in meters per second squared, or sometimes it can be in newtons per kilogram, but that's the same unit. And the height is, or the change in height is always measured in meters. And so this formula here that we're using, this is for objects that are close to the surface of the Earth, or ones where the gravitational field isn't changing much. A key component of solving problems involving gravitational potential energy is you must decide where gravitational potential energy is zero before you start calculating it. And so you're creating like a reference point, or in similar situations with like springs, we create an equilibrium point. So you define in the problem where gravitational potential energy is zero, and then you do all your calculations based off of that. Here we have a book of 1.2 kilograms resting on a table that is 0.8 meters above the floor. We want to calculate the gravitational potential energy of the book when it is resting on the table. And so this is one of those situations where we have to define what zero is. And so we have two choices. I mean, we have many choices, but two that kind of make the most sense. We could say that the book resting on the table here, if we wanted, we could say that the tabletop is zero. That's when the EP is zero. We could define that as zero. And so therefore we would say, as the book is resting on the table, we could say that the potential energy is zero. If we do that, now in part B, it's asking us to calculate the gravitational potential in the book relative to the tabletop when it is on the floor. And so what that means is, if we've defined the tabletop as being where potential is zero, we need to calculate the potential energy on the floor. So delta EP is equal to 1.2 kilos times 9.8, because we're doing it on Earth, and then the change in height is going to be negative 0.80, because it is down 0.8 meters from the reference point of zero. So when we calculate that, we get negative 9.4 joules. I mentioned earlier in the video that gravitational potential is scalar. So the negative sign is not indicating direction in this case. The negative sign is indicating that it's lost energy. And so if the book perhaps fell from the tabletop to the floor, it lost gravitational potential energy. Or likewise, if we had defined the floor as being zero, then to raise it up, we would have to give it 9.4 joules of gravitational potential energy to be at that height. And so that's a key component of energy problems here. The negative doesn't indicate direction, it indicates loss of energy. This next example, we have a block of 2 kilograms pushed to the top of a smooth ramp that makes an angle of 30 degrees with the horizontal. Determine the gain in gravitational potential energy. And so the key word there, smooth, that indicates that we can consider this to be frictionless. So we're not worried about friction or anything like that. And so if we want to calculate the gain in potential energy, when it's at the top here, so once the block reaches the top, we just only look at the height. We don't really need to know about how long the ramp is, because if we're just talking about the gain in potential energy, we're just talking about the vertical height, the change in height. So we don't need to worry about this 3. And so in this case, the gain in potential energy is going to be mg change in height, and in this case, it's going to be 2 kilos times 9.8 times the change in height, which is 1.5 meters. And so we don't need to worry about the angle, and we don't need to worry about the ramp. And so we get a change in energy of 29.4 joules. And that's positive, so this box gained 29.4 joules of energy. And it's interesting to note, it doesn't matter how long the ramp is, it doesn't matter the angle of the ramp. All we're really concerned about in this case is how high the ramp is, and that can tell us the gain in gravitational potential energy. So in summary, gravitational potential energy is due to an object's height above a chosen reference point. So that's part of your setup of your problems. You have to define where potential energy is zero. Negative change in gravitational potential energy represents a loss in energy, and then gravitational potential energy is a scalar, and it's measured in joules.